So, hello everyone, good evening, and we are back again. It's Saturday, and we have with us Madhav, and Madhav is for all that I remember of Madhav is him entering the India Today office where we were at Learn Today, and he was a young entrepreneur who wanted me to see a maths product, a software which he had created, and it was super amazing. And I'm not so good at maths, and I pretended I understood everything and I knew what he was talking about, but it was a fantastic sort of a platform for children. And Madhav has been away. He always wanted to do pure maths. And every time we would ask him, what do you want to do? He would say, I'm looking for some masters in pure maths. And he got that. And he was away in Arizona for a lot of 5 years, he said just now. And he's back in India. And very soon we will see some entrepreneur of the year or Forbes under 30 or something, where Madhav will surely be featured. So today we are dedicating this entire session for our community where we are talking about thinking like a mathematician, and no better person than Madhav to introduce that to us. Over to you, Madhav, and I will try and comprehend what you're saying. Over to you.
No, nothing complicated. Don't worry. It's very straightforward.
Okay.
Thanks. Yeah, my thing can be shared.
Yeah, there is a share button. Yeah.
I have it. The default. Yeah. Okay. Yeah. So thanks a lot, Deepthi. I haven't met Deepthi in a while, but great to meet her after so long. I hadn't heard of the organization, but it looks quite interesting till when I got to take a look at it. So today I'm going to be talking about thinking like a mathematician. So to start with, what does that mean? So in order to answer that question, let's start with a question which is a little more foundational, which is why learn mathematics? Right? I'm sure many of you may have thought of this before, but mathematics, for instance, helps in for your career. So if you want to be a programmer, you want to be a mathematician, you want to be a physicist, you want to do a lot of professions related to biology, whatever, you need to understand some mathematics, right? But that's not all there is to get out of mathematics. Um, the other important thing, which is important even for those of us who decide that they don't want to pursue mathematics in any formal sense or even as related to a profession, uh, there are certain thinking tools and abilities associated with how mathematicians do mathematics. Um, these are uh, things like rigorous reasoning, and then there are a bunch of other thinking tools which I'm going to be touching upon here. There's also a lot of creativity associated with mathematics, and that's something which is going to be outside of the scope of today's discussion. It'll come in parts, but that's not the focus. So, if you think about sorts of mathematics which is done in schools, it tends to be problem solving of problems where the students have either a template or an algorithm, and they're just following a set of rules, or maybe doing a little bit more than that. If you look, say, in ninth grade in India, people do Euclidean geometry. In that, you learn how to prove things, but even that, the sorts of proofs that you do are very um, similar to other proofs that you've seen. So you don't have to actually come up with anything. If you look at the work of people like or you look at um, the more innovative mathematics curricula, they tend to focus on things like proving and maybe on conjecturing, so coming up with statements in mathematics and proving those statements, and on rigorous reasoning and stuff like that. So my focus is actually there's already a lot of good work and stuff like that, and I will put some recommendations at the end of this presentation on things like proving and conjecturing. But my focus is on, and this is the focus of my PhD thesis, on thinking tools which go beyond uh, just plain conjecturing and proving. Okay. So now, what exactly does that mean? I think rather than going into what that entails, let me take you through some examples that might be a more uh, uh, stra- uh, useful way to go about this. Um, okay, so I'm going to start with a question which you might have heard a kid ask um, in maybe in the fourth grade, or a kid disagreeing with you when you read out something from a textbook. So if you ask the question, should a square be a rectangle, or is a square a rectangle? Young kids tend to say no before they've read a textbook, and the textbook says yes, right? Textbook says the square is a rectangle, and young kids say a square is not a rectangle. So, well, one way of responding to kids who say it's not is it's written in the textbook, um, and so therefore you better believe that it's true. I'm assuming everybody in this who's watching this would not find that an acceptable strategy to use. Um, so then what we need is a rational justification for accepting one of them, not necessarily the one that you believe, but one of them and rejecting the other, right? So this is not a typical question which you would see in mathematics, because usually questions which are in mathematics are of the form where you will have a solution or you have to prove a statement or something of that sort. Here we are asking about the basic objects that we're working with and how they should be defined, right? So let's see what's at stake in this question. In this question, we are comparing two classificatory systems. The one on the left is the one where a quadrilateral is just a four-sided uh, figure with straight line sides, for who know that. And in the first way of thinking about it, where squares are not rectangles, this is what a fourth grade kid would believe. Where squares are not rectangles, this is the classificatory system, right? So you have quadrilaterals, and one type of quadrilateral is a rectangle, and a different type of quadrilateral is a square, right? So squares are not types of rectangles. This other system here is is a system where rectangles are types of quadrilaterals, right? And squares are types of rectangles. Of course, there are shapes which are not rectangles, which are also quadrilaterals. There are shapes which are rectangles, which are not squares, right? So, so the question is, we have these two classificatory systems. Let's call this classificatory system one and classificatory system two. Being very creative with names. Uh, why should we pick one of these over the other? Not when I say one of these, I'm not referring to one, but either of one or two. Why would we pick one? Why would we pick two? Okay. So let's try and define what a square is and what a rectangle is using both of these systems. Okay. So I'm going to start with two. In this, a rectangle is a quadrilateral with opposite sides parallel and all angles equal to 90 degrees, right? If you've seen, so for people who don't know what, I'm assuming everyone knows what a rectangle is, but that's a rectangle where all angles are 90 degrees and opposite sides are parallel, right? And every quadrilateral with these properties turns out it's a rectangle, right? And a square is a rectangle with all sides equal. So in this system, in system two, this is what is a rectangle is, and this is what a square is. Now let's look at system one. System one, I'm going to go the opposite direction. So I'm going to first start with squares, and I think you'll see why in a second. A square is a quadrilateral with all sides equal and all angles 90 degrees. Okay, so that's a square, all sides equal and all angles 90 degrees. That's the same definition of a square in this system. But in this system, the one on the left, um, the, the problem is that we need squares not to be rectangles, right? In system one, and so we have to exclude squares from the category of rectangle, right? And so we can define a rectangle as a quadrilateral with opposite sides parallel, all angles 90 degrees. So that looks pretty much similar to this. But we have to add in that adjacent sides are not equal, right? So that this side, so for a rectangle, this side should not equal to this side, right? Otherwise, a square is a rectangle. Okay. So so this is what's at stake, right? This is this is one set of definitions, and this is another. They're both perfectly fine definitions, right? They both make sense. They both. So now, how can we choose one over the other, right? And so let's think about that. And in order to see how that works, I'm going to generalize. Well, I'm going to add in more shapes. Okay, I think that makes you see things a little more clearly. Okay, so so the shapes I'm going to add in are trapeziums and parallelograms. So for those who don't know, a trapezium is something like this, where this side and this side are parallel, and there's no constraints on the other sides, right? A parallelogram is one where um, something like this, where opposite sides are parallel, right? So in the, let's call it system 1 dash and system 2 dash, right? In system 2 dash, the trapezium is now a type of quadrilateral. That makes sense. Parallelogram is now a type of trapezium, right? Because trapeziums only have one pair of opposite sides parallel, while parallelograms have two. So parallelograms would be type of trapezium. Uh, Rectangles would be types of parallelograms with all angles 90 degrees, right? As is here, right? So these are the definitions we just discussed. And finally, a square is a rectangle with all sides equal, right? That's the same definition as we had in the previous slide. Okay. So notice one thing we've seen here. So just by doing this, just by adding in these shapes, uh, the uh, the definitions sorry, oh, I wanted to go the other way. The definitions of uh, the rectangle got shorter, right? Over here, you had to say that it was a quadrilateral with opposite sides parallel, and here you don't say that because that information is contained in this. Okay. Now let's look at system 1 dash. Now this gets very complicated. We get a square quadrilateral with all sides equal and angles 90 degrees. And that's the same as the definition we had on the previous slide. A rectangle is a quadrilateral with opposite sides parallel, all angles 90 degrees, and adjacent sides not equal. This is exactly what we had in the previous one. Okay. But now for parallelogram, what we have to do is exclude rectangles, right, in this system. And so we get that parallelogram is a quadrilateral with opposite sides parallel, and all angles can't be 90 degrees, right? That excludes rectangles. And finally, you need to define trapeziums such to exclude parallelograms. And so you have to say that a trapezium is quadrilateral with one pair of opposite sides parallel and the other pair not. Okay. So as you can see, there's a lot more complexity in this than in this, right? The definitions seem more complex, and you have to exclude things which you don't have to here. I'm going to take that one step further and introduce a rhombus. If anyone has any questions at any point, I can comment in that. So please post them. It's kind of useful as we're going along to clarify things if I've gone too fast uh, or whatever else. Okay. So now if we add in um, rhombuses into our system, let's just see what happens in this system. So for those who don't know, a rhombus is kind of like a diamond shape. Okay, opposite sides are parallel and equal. All the sides are equal. So it's a parallelogram with all sides equal in this system. Okay. And so in this system, in now 1 dash and 2 dash, we get that a rhombus is a quadrilateral with opposite sides parallel and all angles equal, and not all angles 90 degrees. Right? Why are we adding this in? We are adding this in to exclude squares from rhombuses because they're in this system they're different. And but what happens here when we add in a rhombus is that now we have to change the definition of a parallelogram, because if we use the earlier definition of a parallelogram, a rhombus remains a parallelogram, right? And so we have to change that definition. In system 2, we don't have to change any definition, and now we get an additional definition for a square, right? A square is a rhombus with um, all angles 90 degrees. And so what we get here is we've actually learned something from this system, that a rectangle with opposite sides, sorry, a rectangle with all sides equal is the same as a rhombus with all angles 90 degrees. These are from the choosing this classificatory system, we've learned something about squares, rectangles, rhombuses. With this one, we don't get any of that. Okay. And we have to do all this additional work here by whenever we add in a new object, we have to go through the remaining objects and see what we need to change in them, right? To exclude that object from the existing objects in our classification system. Okay. So this was an example um, of us answering a question: should X be a type of Y? Right? And that's now a question which comes up everywhere, right? It's a question which comes up in various parts of mathematics, but it also comes up everywhere else outside of mathematics. And so just before I get into things outside of mathematics, let me just summarize the sort of considerations we kept in mind, um, by which we could say that the textbook system, for once, the textbook did a good job and it's reasonable. And so the textbook is the more reasonable system for the purpose of doing mathematics. That doesn't mean it's the best system for every purpose, right? Maybe for if you run a table, you sell tables, and you run a shop to sell tables. For that purpose, it may be useful to not classify squares as rectangles. I don't know. I'm clueless about practical things, but for certain things, you can imagine that it might be useful to have um, to have squares as um, to have squares and rectangles as separate things, right? For certain practical usages. But clearly, for the point of view of mathematics, it seems like we get a lot by saying squares are types of rectangles. We get a lot for free by saying squares are types of rectangles. Which, if we don't do that, we don't get all of that, right? So let me give you an example. If that's the type of rectangles, and we know that um, the diagonals of a rectangle are equal, right? Let's assume we know that's true. we automatically learn that the diagonals of a square are true. If we were dealing with, if squares and rectangles were separate, right? The What you would get there is that squares that you would have to show it to be true for squares separately. You don't get it for free. And the most important thing is to get things for free. I'm sure most people agree with that. And so that's a very important consideration when we're keeping in mind when we're doing we're constructing knowledge of any type, right? You want to do the least amount of work to get the most amount of uh, the most value, right? Well, not just constructing knowledge. I think anything. Um, the other thing we saw was that one system was much easier to define in than the other system. And the third thing we saw was that we didn't really need to change anything in um, the system two um, when we added in new objects, but we did need to in system one, right? And so there's clear um, reasons to choose system one over system two. Okay. Um, so now what I've laid out so far is not something which I would like read out to kids or anything like that. What The way I do this in the classroom is to get students to debate, right? So you start with two possibilities. One is a square is a type of rectangle, and the other it isn't. And you want to come up with reasons for one over the other. At some point, kids get brainwashed by the textbook, and all of them agree that a square is a type of rectangle. So then, if I'm dealing with the brainwash, then in that case, I'll take this side of a square and rectangle being separate things. Okay. And so and I would argue for that position. So that's the pedagogical aspects of this. I have laid this out in reasonable detail with an example of an actual classroom situation in my PhD thesis, which should be available somewhere online. If you Google, I think it's on Google Scholar. Um, Okay. So as I said, one of the most important things for me is not just is doing mathematics, not just for being useful within mathematics, not the outcome, the learning students get from mathematics should not just be useful within mathematics. It should be useful no matter what you end up doing. So here's an example of classification in biology, right? Aristotle's classification of living beings was um, there were humans and animals as two separate things, right? And even in regular language, right, um, humans and animals tend to be different things. Definitely, for instance, in Hindi, you don't refer to when you're referring to a human as a janwar, that's usually an insult. It's not a it's not a descriptive term. Um, Uh, so, um, so the question is, which of these classification systems is better? Aristotle's, where humans and animals are different things, or Linnaeus's, where humans are types of apes, whatever. I don't know any biology, or which are types of whatever, and so on, till you get to the point of animals, and then those are types of living beings, right? Of course, they're living beings which are not animals. And so the question is a human an animal is has exactly the same structure, at least the structure of the question, as is a rectangle. Sorry, not as a rectangle, a square, but is a square rectangle. My handwriting is awful. Sorry about that. Um, is a square a rectangle? So these are the same structure, and in fact, you can make very similar arguments for this system over this system to the ones. I'm not going to work through them in detail right now, but I think you could probably see uh, what those would look like given the argument we've seen so far. Okay. Okay. So uh, now I want to move on to another example. I'm just doing this two examples. So this is the second and last example of these sorts of thinking tools of mathematical thinking. Okay, so here what we're looking to do is take the concept of a straight line and try and make it make sense in places where it's not obvious. Try and extend the concept of straight line from or a straight line segment, sorry, from the geometry you learn in textbooks to other spaces. Okay. So so let's start with, I'm assuming you agree that at least in the geometry you learn in textbooks, this is a representation of a straight line connecting the red point to the blue point, right? Of course, this is not a Euclidean straight line. Euclidean straight lines are um, uh, no width, etc., right? But this is a representation of a Euclidean um, straight line segment, right? And I'm assuming you agree that, so this is a straight line. I'm assuming you agree this is not a straight line segment. I'm just going to use straight line and straight line segment to mean the same thing for now. It's too confusing to uh, keep clarifying that. Okay. So now let's think about some properties of straight lines. They are shortest paths. They go in the same direction, right? They don't change direction. Um, they are unique between 2 points. There'll be one straight line segment connecting two given points, right? And they belong to a unique line, right? There's some line, whatever, an extended thing, and there's every line segment belongs to exactly one line, right? It can't belong to two lines. Okay. Okay. So now I'm going to take the exact same situation we had at the beginning with a red and a blue point, but now there's an obstacle, right? This green obstacle in the middle. And now the question is there a straight line connecting uh, the red point to the blue point, or the blue point to the red point? Does that straight line segment exist? Well, um, if we think about the property of in the same direction, and we use our intuitive idea of what we mean by same direction, I'm assuming you agree that there is no straight line connecting the red to the blue, right? Because you go in the same direction, and then you hit um, the obstacle, and then you can't. Um, Assuming our naive usual notion of direction. Um, the However, if we take shortest path as our concept of straight line, well, there probably is something. There is some shortest path between these, maybe uh, uh, between the red and the blue, right? That it may not be exactly the one I've drawn, but there's some shortest path of between these two points, right? So notice here that if we want straight line to have all the properties it had in Euclidean geometry, we can't do that, right? Or it's not that we can't do that. Then we have to conclude that straight lines don't exist. However, if we ignore certain aspects of straight lines and keep others, there is one concept of straight line, that shortest path, which does allow us to have um, allow us to have straight lines in this space, right? Actually, I want to add in another property here, which I forgot to add, which is uh, that there always exists a straight line between 2 points, right? I don't have that here, but in this one, oops, sorry, in this one, there will always exist a straight line between 2 points, right? It may be weird, but it'll always exist. In this one, that's definitely not true, right? These 2 points don't have a straight line between them. If we want same direction, okay, unless we change our definition of direction. But just for now, that's the definition we would go with. Uh, and over here, there, if the straight line exists, it'll be unique. Okay, in the same direction thing. You can think about that. It's fine if that's not completely clear. In this one, it's not clear whether they'll be unique, right? In fact, you may think of, like, for instance, this one, right? So, which may have the same length as the one on top. And just eyeballing stuff here, but this one may have the same length as the one up there, right? So, so this still has two properties of straight lines, but doesn't have the other two, right? Wait, there were five. Um, Belongs to a unique line. I'm going to ignore that for now because we don't know what a line would look like here, right? So let's ignore the line one. But out of the remaining four properties, this all the straight lines which exist here have two of those properties, and here they also have two of those properties, right? But we have to now make a choice. Now, what is the basis of this choice? I'm not really going to talk about that today, but let's continue and take another space. It's right now. I'm just raising the question. Um, so now this is this thing called taxi cab geometry. Some of you may be familiar with it. If you're not, it's very easy to conceptualize. So think of a grid city, right? There are buildings here, uh, whatever, in the blocks, right? Kind of New York City type thing. And these are the intersections, and these are the roads. They're very faint, the lines, but hopefully you can see them. The little lines are the roads which are connecting the intersections. So now you can't go through the buildings if you're a taxi driver, so you can't go between the buildings, right? So if you want to go from the red point to the blue point, you can't like go through the. You can't take, say, you can't take this path, right? Because that's through the buildings. You can only go on the roads. Okay. So here, very clearly, the shortest path, the path in the same direction, both of them um, are this path, right? The path on the same block, I'll say on the same whatever street. So the shortest path, or the path in the same direction connecting the red point to the blue point, is this path which I've underlined in purple. Okay. So um, so the question uh, here is, so now let's take actually another example in taxicab geometry. Oops. Now let's think about this one, where the red is here and the blue is here. Sorry, actually. So the blue point is here and the red point is down there, right? And the question is, what are the straight line segments between these 2 points? Well, if we want something in the same direction, well, that doesn't exist here. Assuming by direction we mean what we would think we would mean, um, in a city, the cardinal direction. So you put a compass and you look at what it says. And so clearly, this is not possible, right? Because you're going through the buildings. Assuming we can't go through buildings, this is not possible. So there's no path in the same direction connecting the red point to the blue point. However, if we think about what are the shortest paths between the red point and the blue point, there's lots of them, right? There's this one on top, right? This one here. There's this one here. There's also this one here, right? There's the one going at the bottom, right? They all have the same length, right? You're going 1, 2, 3, 4, 5, 6, 7, 1, 2, 1, 1, 2, 3, 4, 5, 6, 7, and so on. So all of these will have the same length, right? Because you're just going 3 up and 4 across. You can do that in many ways, right? And so if we once again, if we take the concept of straight line as shortest path, they then straight lines exist between any 2 points in this grid city, and uh, but they may not be unique, right? However, if we want same direction, as our concept of straight line, then there are points between which they don't exist. Um, but when they exist, since they will only exist in situations like this, they're always unique, right? And so once again, we have this give and take between these two concepts of two ways of generalizing the concept of straight line, one as shortest path and one as um, uh, same direction. And by one of them, we get certain properties preserved of straight lines, and by the other one, we get other properties preserved of straight lines. Okay. So now let's think about straight lines on a sphere, right? So on the Earth. So when you if you fly um, over continents from one continent to, like, say, across, you go from, say, Delhi to Buenos Aires, you're going to go um, over a very odd looking path, right? When you see it on a flat map, it looks like you're taking some weird path. You're not going what looks like the straight line path, right? What you're doing is you're taking the shortest path, right? You're going on one of these great circles, what they call great circles, right? They are shortest paths, okay? Even though when you flatten them, they don't look like shortest paths. Right? Flatten them in certain ways, they don't look like shortest paths. Um, Between 2 points. So if your red point is here and your blue point is here, this is the shortest path between them, right? And if your red point was here and let's say a blue point is here, now there will be a great circle which will look probably something. Oops, let's take that. Probably something like this, right? Which will connect the red point to that's going behind. Sorry, I can't draw. So this is going behind. So connecting the red point to, well, that blue point kind of disappeared, but to that blue point, right? So that's the shortest path. Uh, Sorry, that's the shortest path between the red point and the blue point is these things on top, right? But now notice that if you take points on opposite sides of the Earth or of a sphere, so say you take the North Pole and the South Pole, there are now an infinite number of uh, straight lines connecting them, right? Any longitude, for instance, if you have the North Pole and the South Pole, uh, any longitude is a shortest path, right? So I think I have a picture. So all of these are shortest paths, right? And so the question becomes um, that so now we can't the point becomes that we can't preserve the concept of uniqueness, which was one of the properties that we had of straight lines. But we can preserve direction and shortest path, right? Because this seems like saying that it's in the same direction, right? Going on a longitude, if you define direction in the right way, it would be the same direction. Okay. This is assuming you can't go through the Earth. Okay. All of this conversation assuming you can't go through the Earth. You can only go on the surface. Okay. So, so the important things about here are sorry, that the important things to think about here are uh, we had a concept which we understood quite well, at least at a conceptual level, we understood it quite well in a particular area, right? In, say, Euclidean geometry. But now there are things which look similar to Euclidean geometry. There's some geometry going on, right? On a sphere, there's some geometry going on in the grid city. There's something similar to Euclidean geometry, right? But it's not the same. And so, can we import concepts from Euclidean geometry to these spaces, to whatever spaces these are, whatever um, spaces we're interested in? In order to do that, we have to make compromises. We have to lose certain things. We have to choose between certain things, and so on. And that will so those are the questions which need to be asked as to what you want to preserve, you're willing to sacrifice when you're moving from sounds very dramatic, but when you're moving from one type of geometry, when you're moving from one place to another and you want to import a concept, right? Maybe there are times when it like perfectly imports, but that's probably not going to be the case for anything interesting. Okay. Um, oops. Okay. So now, once again, I'm going to use biology a little bit to talk about how this relates to stuff outside of mathematics. So now, people talk about biological evolution. People have been talking about biological evolution since before Darwin. Um, and cultural evolution is something which is, I think, slightly newer uh, in the in academia than probably maybe 100 years old or something. I'm not sure. I have no clue. I'm just making things up. Uh, so, um, so cultural evolution. So the question is that we start with biological evolution. That's something we have some handle on. We have some idea of what it is, right? You have some idea of species, right? In biological evolution, you have some idea of species speciating, so new species coming into existence. Uh, Concept of ancestry, and so on. There's a bunch of different things which concepts which exist in biological evolution. So now, when we move that to asking about cultural evolution, move from asking about biological evolution to cultural evolution, we probably can't import. I haven't done this, but we probably can't import every single thing from biological evolution to cultural evolution, right? Well, the genes won't be exactly, there might be something like genes, but they won't be exactly the same, right? Well, I think Dawkins suggested memes are the equivalent of genes. Uh, but but whatever, they're not exactly the same thing, right? So there's some compromises you're making with the concept of, say, gene to extend it into this new area, right? And so the question here, as it was in the case of the geometry, was that what should we preserve and what are we willing to let go, right? In the concept, in order to best understand whatever we are trying to understand. Okay, cool. Yeah. Okay. So that's kind of what I wanted to talk about in terms of examples. Uh, from here, what I wanted to, I think, end with is um, uh, what are other aspects of mathematical thinking, which, so far we've talked about two things. One is classification, and the other is extending definitions um, outside of their initial whatever space of where they've been defined, or initial where whatever they've been defined in, and we're trying to extend it outside of that, right? Okay, so so one type of question is, should an object be part of our inventory, right? So going back to shapes, uh, we have trapeziums as part of our inventory, right? We have one pair of opposite sides parallel. They're part of our inventory. Why isn't one pair of no, say one two sides equal, a quadrilateral with two sides equal? Why is that not an object which we study? So let's say this quadrilateral, right? This side and this side, assume they're equal, right? Uh, why don't we study shapes which have that characteristic over shapes, but we do study trapeziums, right? Maybe there's no good reason, right? Maybe it's just historical accident or whatever, that doesn't matter. But if there is a good reason, we should think about it, right? So why? So the question is, maybe we should be studying these shapes, and maybe we shouldn't be studying quadrilaterals. Say, shouldn't be studying trapeziums. Either way, it's a question which we should be asking, right? Should Why should certain objects be part of our inventory of things that we study, and on what basis should we make those decisions? and why should other objects not be part of our inventory, and on what basis should we make that decision, right? We want to be able to justify even questions of that nature, not just questions like, oh, squares have um, diagonals, equal diagonals. Sure, that's a claim which once you have the definitions, you just need a proof. But we also want to justify things which are about the nature of the foundations of our uh, of whatever theory we are working in, right? In Euclidean geometry, etc. Uh, why do we have certain objects but not other objects? Okay. Another question is, which definition should we choose from various options? We kind of did that when we talked about extending definitions. Which what should we preserve, what should we not? But even more generally, sorry, there is if we define a triangle to be three vertices, right, and the straight lines which connect them, then this, I'm going to draw this on top, is a triangle, right? A, B, C. The three vertices are A, B, and C, and the three straight line segments which connect them are A, B, B, C, and AC, right? These are all straight line segments. They connect these, and it looks like it is a triangle, right? But it has zero area, etc. There's another possible definition of triangle where you exclude this by saying all the three vertices should not be collinear, right? They shouldn't be on the same line. That just instantly excludes this. Okay. So why should we pick one over the other? Right? Why is one definition better than the other? Okay. Then is a given proof which we've written, is it sufficiently rigorous? Because um, if you haven't, you should um, read Keith Devlin's article on when is a proof. I think is the article. He's asking the question as he's asking the question, at what level of rigor is a proof acceptable? Of course, we're not talking about computer proof checkers and stuff like that here. We're talking about when humans read other humans' proofs. What level of rigor is a proof acceptable at? And he works through. He kind of. Um, I'm actually not going to go into that. I think he does it way better than I would. So, Keith Devlin's article, "When is a proof?" is definitely worth reading. Uh, then there's a question of which proof is better. So there are certain proofs which, when you read them, I don't know if any of you have had this experience, that when you read a proof, you get some sort of insight, some sort of like deep insight into mathematics, into what's going on, right? And there are other proofs which you work through them carefully, you spend hours working through them, and you understand nothing. Like all you're doing is like, you understand what you're doing, but you don't get any insight from it to take forward anywhere outside of that particular thing. And so there are certain proofs which I think pretty clearly you can say are better than some other proofs, and there's some which are kind of on the fence. I would be on the fence on. So maybe this could be rephrased as, which proofs have better explanatory value, right? And what do we mean by explanatory value? Then the another question, the last one I'm going to discuss here, is what should we choose as our axiomatic system? So given I, uh, for instance, for Euclidean geometry, there's a bunch of different axiomatizations of Euclidean geometry. There are a bunch of different axiomatizations of set theory. And when a kid is doing it, we can actually get. I've gotten students to create axiomatic systems for certain spaces where I've given certain constraints on, and they construct axiomatic systems. Um, like eighth, ninth graders, they're definitely capable of doing that. Um, and they're kind of doing this intuitively. These things which I'm asking here. Uh, yeah, so there's a lot of things which I think we can do with kids, even younger than eighth, ninth grade. I think some of the things which I've talked about here, maybe for eighth, ninth graders, the amount of spam you get is really annoying. but uh, eighth, uh, eighth, ninth graders is what I've been doing this with. The sorts of things I discussed today, um, and they're definitely capable of it. And younger kids are capable of a lot more than I think we give them credit for. Uh, and I would definitely think about these things, including them in um, teaching. Uh, as you can see, the goal of education I have here is slightly different to maybe what many school systems have. I'm actually not interested in them understanding Euclidean geometry. I really don't care if they understand taxi cab geometry. It doesn't bother me because that's really not going to be useful to them 3 years after they finish learning it for 99% of students. What I care about is that they walk away with certain ways of thinking and certain mindsets associated with thinking, which then can hold them in great stead, whether they're deciding to go cast a vote, whether they're deciding to um, figure out what doctor's prescription to take seriously if you have two doctors who are giving two different things. Uh, how do you decide between them, etc. So various decisions that you're making in your life 40 years after you finish school, uh, your education should be valuable for that purpose, right? Not for the purpose of understanding Euclidean geometry, which is going to be useless to you in a few years. Okay. Okay. So, just on these sorts of things, I've discussed them a bit in my PhD thesis, which once again just on it should be on my Google Scholars page. You can probably Google that if you're interested. It's very long, so yeah, it's probably not worth going through in that much unless you really have a lot of time. Uh, okay, and okay, so finally, I just wanted to leave you guys with some resources. So I started writing um, on mathematical thinking. I write 1 to 2 articles a week, which available on that link. Uh, Think is just quickly to tell you about Think. Think is an organization. Um, uh, there, there's a few of us who started it in 2014, and we run courses every year and so on. And the goal is to help students think like mathematicians, scientists, philosophers, historians, and so on. It's broader than what we were discussing today, which is just on mathematical thinking and a little bit beyond that. And finally, some books which if you're interested in these sorts of things, Polya was always great to look back on, if you read Polya or not. And a lot of people have read Flatland. If you haven't, you should pick it up. And Ian Stewart's written Flatter Land, which is also worth reading. It explores some of the things that we're talking about. Not a lot, but some of the concepts. Yeah. Okay, that's it. Deepti.
Thank you so much, Mother. I think this is something that I understood, so I'm sure our community did as well. It's usually what you say just zooms past 1 kilometer above my head, but this was really good. This was really good, and I can see how your thought process has evolved. I mean, you were what you are. I mean, just what you are right now as well. Can I get you down to maybe the lower grades? You know, when you are talking about inquiry, and you're looking at. I mean, this was just phenomenal. The debate part of it, and
Yeah.
improving things and all. So
Mhm.
there's a question. It's not on Facebook or on our YouTube channel. It's somebody's just messaged it to me on WhatsApp, and it says. What would you suggest are the strategies? Just tuck tuck tuck, 5 or 6 of them. How would you get children to start thinking, not only just geometry, but suppose,
Mhm.
let's say, they're starting on fractions? So what would be
Yeah.
your strategy to get them to think?
So I think one of the things which needs to be done at younger grades, which I've worked a little bit on, but not a lot, is getting students to do mathematics as science. By which I mean, in mathematics, you want arguments, right? In science, you want to explore. right? You want to do empirical work, like trying things out in order to come to conclusions. So say for instance, I were to ask the question, um, take a cucumber and tell me what the cross sections look like. You first imagine what they look like, and then you think about, and then you cut it to check, right? So if you're using your imagination, you're visualizing stuff, and then you're actually checking, right? Then make sure it doesn't happen without the visualization. Otherwise, it's pointless. If they're just cutting cucumbers, that's just fine. That's good for a meal, but it's not useful for learning. In terms of like numbers and things like that, I've actually written a series of articles on numbers, and this it's not meant for young kids to read, but I think some of the ideas can be used there, which is that my concern with when numbers are introduced to kids is numerals are introduced to kids, and then they confuse numerals with numbers, right?
Hmm.
That two that you see is not the concept two, right? Two-ness is a concept which is not the numeral two, right? You call it do in Hindi. They have the two lines in Roman numerals. Those aren't what two is, right? Two is a concept, and those are just representations of that concept. And
Right.
so I think working more and more with younger kids to do using dots and lines and stuff like that much longer than is usually done
Yes.
before you introduce numerals, so that they actually get a deep. You can do multiplication with dots and lines, you can do division with dots and lines, you can do addition and subtraction. So you can do what you would do till the fourth grade. You can do fractions with things like that. What you do till the fourth grade, you can do maybe earlier on, but without actually algorithms and numerals and stuff like that, just with dots, lines, objects, blocks, whatever they're playing with, things like that. Yeah.
Sure, sure. Even our curriculum is called Create. It's an acronym, and
Hmm.
we also, the numberness. And Sonali Bhatt, of course, I don't know if you remember her. She's also from Vasant Valley.
Okay.
She
Yeah.
is,
Okay. Mhm.
yeah, so she's the early years expert in Mahatattva. So she also talks about how you get the children to write one 100 times, and then two 100 times, for them to understand what one and two is. And if you tell them, go get me two things from that table, they don't know what two
Yeah.
means. So
Yeah. Yeah.
yeah, so I agree on that, and that is something we should stress on. And I think with NEP coming in, and people trying to get
Hmm.
more experiential learning and more hands on, I think there should be a difference. And
Yeah.
we will be making progress in that. So there are a few people who are since last year, when the NEP was being drafted, we've started our own journeys at different stages, trying and implementing what NEP actually means in schools. And it's really heartening to hear from the schools where we are implementing our curriculum, that actually, what NEP is talking about, we are seeing that in our children. So,
Hmm.
Madhav, thank you so much for
Right.
doing this session for us. There is also a message from the HOD Maths and Computer Science in DPS. I think he's computer science, and he's asking me, who is this guy? So you have made an impact, and if he's listening, Madhav is one person who is absolutely brilliant in what he does, and we hope, Madhav, you create series for the little children as well, so that that fraternity is benefited as well. Thank you so much for your time, and
Yeah.
all the very best for your journey back in India. And we
Thanks.
hope to see great things and visualize great things for you. Thank you for
Thanks.
joining.
Thanks a lot. I've enjoyed this a lot. Thank you.
Great. Thank you so much. Bye bye.